This video will begin to prepare you to learn to install the servos and use the PULSOUT command. Let's go ahead and start learning how to use the PULSOUT command. The PULSOUT command has the syntax pulls out, pin, and duration. The pin is in reference to which pin, P1 or P13 or whatever you're using, for the power, and how long you want it to occur. Now this can get a little tricky. The duration is in milliseconds, but it's a little different. It actually uses microseconds. Okay, let's go ahead and check this out. Down here toward the bottom of page 36, you will see an example of how to do 0.13 seconds. What you do every time is you do 65,000, which is the number you can put for the duration, times 2 microseconds. This makes the duration of the pulse be 0.13 seconds if you do the math on a calculator. The program we're going to try to do is to have a pulse of 0.13 seconds with a pause or low voltage of 2.0 seconds. Now again, the micro is a letter mu or mu, some people pronounce it, and uses the Greek letter which looks kind of like a U with a tail on the left. So for example, 8 microseconds would be 8 mu seconds. Let's go ahead and try 65,000 for our new program. Our new example program we're going to try is Pulse P13 LED.bs2. Again, a 13 is in reference to which pin we're using, and 0.13 seconds. So first, we're going to have a debug message indicate program running, and then simply we're going to do a do loop with a pulls out command on pin 13 for a duration of 65,000, which is equal to 0.13 seconds, and a pause of 2 seconds. Okay, so debug command, again, program running. Now you can add in extra lines or don't, it really doesn't matter. We're going to do our do loop, starting with our do, and then pulls, PULSOUT, space. Now we need 13 for pin number 13, comma, and then our duration. In this case, our duration is 65,000. Enter. We're going to pause for 2 seconds. Now this 2 is in milliseconds, so remember this is times 1,000. And then we're going to loop it. Let's go ahead and make sure we do our save file. Save as. Make sure we turn on our switch and click download. Okay, so notice that there is a very short number of seconds where the flash is occurring. So a quick amount of voltage up and then a pause in between. Pretty good. All right. Now, what you can also do is pulse both of them. This is similar to what we did before, where this time you can have a new program or you can just use the same one. It's up to you. You can make it pulse both LEDs if you want to do that. It should be fairly obvious what to do though. Pulse LEDs.bs2. Okay, save as. All right, let's go ahead and do our debug command again. Now this time we're going to have program running, same thing. Again, do our do and our pulse out 1365,000. And then we're also going to do pulse out 1265,000. And then we're going to pause it for 2 seconds and loop. Save file, download. Let's see what happens. Okay, so notice what's happening here. You have the number 13 occurring first, then number 12 occurring after. That makes the lights happen not necessarily simultaneously, but happening one after another. You can see this in a diagram. 0.13 seconds on for P13, and then notice that 0.13 seconds is actually located just at the end of the pulse for P13 for P12. Okay, let's make this a whole lot faster. Let's just remove one of the zeros. And then we'll go ahead and make the pause even shorter as well. Save, download. Okay, so it's just going a lot faster. You can even do it again if you really wanted to. Remove more zeros. Same thing. Okay. Now we could even try changing the argument where instead of having two different ones, or instead of having the same ones, you can have two different ones. Get rid of that extra space there. Doesn't really matter, right? Download. Might be a little hard to see on the camera, but one is a little bit different than the other. Now we can even do 750 to make it the same, and I don't know. It's basically the same thing over and over again. Now, of course, you can have some fun with this. Let's say you make one pause first. Let's do maybe 200. And we put the other one, let's try 1,000 for each. Oh, let's do another pause. Okay, so this is just for fun. This is not necessarily in the book, but you can check it out. So now they're alternating, right? So left and right, left and right, left and right. So by doing different orders and pauses of the commands, you can make different things happen. Now, what if we made these try to line up somehow? I don't know. Let's say 800. So a little faster on one, maybe made the pause a little different. So you can make the rhythm and the lights occur in varying fashion. Okay, let's go and turn this off for a second. All right, let's go ahead and start on activity number 3, connecting the servo motors. At this point, you're going to need the servos, which is this item here. Don't take anything apart from your LED board, Board of Education, with your resistors and all that. You still need all that directly in place how you have it. At this point, because you have a Board of Education, you're going to go to page 42, which is just directly the next page. Okay, so again, it asks you to turn off the power, and then scrolling down, you're going to connect your servos to the board. So what you're going to do is take your cable, okay? Notice that there's a black, red, and white set of cables, and you're going to plug it into um, the one that says 13 and 12 at the top here on the right. Okay. Now make sure that the white is facing toward the top of the board, and you just gently slide it in. Now go ahead and take a second servo and do the same thing on the other side. Okay. All right. So notice the numbers that are up above the board. Um, 13 is in reference to P13 and 12 is in reference to P12. So you want to pay attention to which servo is in which slot. One thing that you can do as a tip is to somehow mark which servo is on the right and which servo is on the left. In this case, we used some tape with a pen and just indicated which one was which. Okay, so it shows you a picture of what it should look like all together here. And again, you should have the LED circuits from activity number 2 still put together. And so we're going to move on to activity number 4 on page 49. So you're going to need this screwdriver. If you don't necessarily have this screwdriver, which has a cross pointer Phillips and a flathead on both sides, you can get any Phillips number 1 point screwdriver with a 1/8 inch shaft. However, I've found that this screwdriver works pretty good, or you can get an even larger one, which can help with some of the turning to make it even more precise. One way or the other, make sure it's fairly pointy and not necessarily flattened out on the ends. Okay, so what we're going to do is we're going to send a uh, signal of 1.5 millisecond pulses to each servo. Okay. Now, what we want is for these pulses to go to the servo, and once it does, it should make the servo stop if the uh, potentiometer is the correct setting. Okay. All right. So we want 1.5 millisecond pulses. So 1.5 milliseconds, if you put in your calculator, is 0.0015 seconds. And we're going to divide that by the 2 microseconds for the calculation for the pulls out command, which is 0.000002 seconds. And so you divide those and you get a pulse duration, or excuse me, duration argument of 750. So we know we need 750, and we're just going to start with a pulls out 12 command of 750. Okay, so let's go ahead and start a new program called Center Servo P12.bs2. Okay, and so what we want to do again is indicate that our program is running. So we're going to have a debug program running. And again, we want a do and loop command, in this case with a pulls out of 12 comma 750 and a pause of 20 milliseconds. Do pulls out of 12 and 750, pause of 20 milliseconds, and loop. Okay, so save this, download it. Oops, make sure you turn it on. There we go. Try again. Okay. So mine have already been centered previously. Let me show you what's going on. What you're going to do is you're going to take the Phillips or cross point side of your screwdriver, and you're going to take the one that is in number 12, which should be the one on the right. And you can then flip your servo up, and you should see this little uh, screw, or yellow screw inside the blue. All right. Now, once you send it, do make sure you turn it to number 2. Okay. So you'll see the LED is actually flashing here. And so this is indicating that the power is on. And this is how we're going to note the pulses to the servos. Okay. So if I rotate the screwdriver, you'll see that I can actually determine which direction it's facing based on the potentiometer, that little screw in there. I'm going to then turn this ever so slightly until it no longer moves. Be careful, only tiny little movements can cause it to start moving. Notice how when I pulled out my screwdriver, it actually started moving because I bumped it. Be very careful. All right. So we've successfully centered one of these servos. Now what you're going to do is go ahead and switch it back to the number 1. Go ahead and change your program to number 13 instead of 12. Save and download, and the other LED should flash on, and then you're going to go ahead and do the same thing with your other servo. Use the screwdriver until it no longer moves. Again, make sure that you have it on number 2, so power is sent to the servo. Adjust, and then when you're done, shut it off. Okay. At this point, you've completed activity number 4. And so now you actually don't need any of the servos or anything in order to learn this new set of programming. But you can just go ahead and leave it together if you want. It doesn't really matter. Okay, at this point, you're going to learn about variables. Now, there are 4 different variables. In math, we use variables like x, y, ABC, and then in science, sometimes you'll see even Greek letters getting used. So in programming for a computer, basically there are only one set of variables you care about, and that's called a bit. A bit is a series of zeros and ones. Typically, we hear this is called binary code. 0 means off and 1 means on. Specifically, the power being turned off and on. However, there are actually 3 other types of variables besides a bit, but it includes a certain number of bits, so they're all related. A nib is 0 to 15. A byte, which is considered technically 8 sets of bits, is 0 to 255. And a word is from 0 to 65,535. Or, if you split that in half from a number line, negative 32,768, including 0 up to positive 32,767. What we're going to try is a word type of variable. The syntax is you give the variable a name. It doesn't matter the name you give it. Then you have a VAR indicating that you're using some sort of variable. And then you use one of the size words, bit, nib, byte, or word, and you place this here. After you tell the program what kind of variable you're using out of those 4 sizes, then you declare the variable, meaning you set the variable to a specific value. Make sure that you use the correct variable size depending on the number you want. For example, if you're doing 500, like we're going to do in the example program, you need to use a word variable. But if you are using 0 to 200, you could use a byte or a nib for 0 through 15, or a bit if you're only going up to 1. Now, you can also indicate multiple variables at the same time. So we're going to go ahead and do 2 different variables. Both are variables using word, and we're going to give them the name value and another value, where value is 500 and another value is 2000. The numbers themselves don't really matter. The point is just to explore this type of programming. Also, we're going to use that times operator that we tried in the original training that we did. Okay, let's go ahead and give this a try. Our example program is going to be variables and simplemath.bs2. So let's go ahead and do a new file. save as, and save the name. Now we're going to do, before running the program, predict what each debug command will display. Let's go ahead and try this. In the program, we have debug question mark value. Okay, so far it looks like we have value and another value where we have a word size, which declares the variables. Then we have a value of 500 and 2000 for initialize the variables. And then we're going to display the values. So it seems like we're just going to have the debug terminal indicate 500 and 2000 and just display them. Then it looks like we're going to take a new value by replacing the original value of 500 and saying that the new value is now 10 times the number indicated for another value, which is 2000. We're going to have the chip perform an operation, and then the debug again for the same thing should display values, but hopefully the value variables should be different. And then we're going to end the program. Okay, just to make this easier, I'm going to go ahead and just copy this and put it in. Save, turn on to number 1, and download. Okay, so I can turn this off. All right, so notice that what happened was it showed us value of 500 and another value of 2000, which is what we indicated it should be. And then the new value was 2000 times 10, which is 20,000, and display another value one more time of 2000. So fairly simple exercise just using the variable commands. Okay, so the book goes through and shows you what's going on there. Okay, so let's go ahead and try this again. But this time, we're going to have it do a subtraction. So instead of having value equals 10 times, we're going to have it do value equals value minus another value. So notice what we're doing is we're using the value originally of 500, subtracting it with another value, and making value now a new number. We also want it to display the values again, but this time we're going to have it use the SDEC value. Now the SDEC formatter, we used a similar one called DEC earlier. And so this is just a simplified version of showing a number. Okay, let's go ahead and replace in my screen is lines 11 and 12. Save, make sure our board is on to number 1, and download. Okay, so it looked like it worked. Value was 500 originally, became negative 1500. Another value showing 2000 each time. So we're good. All right, so counting and controlling repetitions. The most convenient way to control the number of times a piece of code is executed is with a for next loop. All right, so we've got a new loop. Instead of do and loop, we're going to have for and next. So the syntax is for some sort of counter argument equals a start value. to an n value. Now notice this new set of programming. When you see something between curly braces in a syntax description, it means it's an optional argument. So this means you don't necessarily have to include it, but you could if you need to. All right, let's go ahead and try a simple one. Count to 10. So we're going to have the program count to 10. So new file, count to 10, and let's go ahead and use our for and next statement. Ready? So for. Now counter can be any counter you want. You don't have to necessarily name it counter, but the book has you call it my counter. So again, it doesn't really matter. Equals 1 to 10. So starting, ending. Next line. Now we want the counter to go from 1 to 10. We want the debug terminal to show what my counter is doing. So question mark to indicate showing this variable, my counter. And we want it to pause for 500. And then at the end is next. At the end, what we want it to do is perform the next thing on the list. So we're going to have it do a debug CR, telling us that it's done counting, and we want the program to end. Save the file, turn on our Board of Education, and click download. Okay, so it looks like we got a little bit of trouble here. It says expected a variable. Sometimes, if you forget, it will indicate a syntax error. In this case, I forgot to include to name my counter. So let's go ahead and add that in before. My counter is a variable. Now again, because we're doing 1 to 10, we didn't necessarily have to use a word variable, but let's just go ahead and use a word variable. Okay, so again, just to showcase, if that happens, you maybe missed a step and the program was looking for something, and so you go, oh, I forgot. Let's go ahead and add that in. Save it successfully, meaning there's no syntax problems. Download. All right, you can see my counter counting from 1 through 10, stopping at done, program is done. Okay, your turn. Let's go ahead and try for our next one, my counter going from 21 to 9. And we're still going to pause for 500 and see what happens. All right, save, download. All right, so it looks like this one is counting down from 21 down to 9 and finishing. Great. Now we can go ahead and also include another thing at the end, which is a step value. We can cause the counter, in this case, the for next, to do steps instead of going one by one automatically. We can have it do step by 3. Save and download. And there you go.